Hi, welcome to the Apache Druid notebooks. My name is Sergio Farragut, and in this sequence of videos we're reviewing secondary partitioning. In this particular one, it's the second of 3 videos where we're looking at hash partitioning. So let's get started. So hash partitioning is another kind of secondary partitioning that you can use in batch ingestion in Druid. It provides some benefits over dynamic partitioning in that it can do perfect rollup. We'll talk about what that is. It can provide some partition pruning at query time, which improves query performance. So that's a good benefit we'll talk about. It's slower at ingestion than dynamic partitioning. It has to do more work, and we'll talk about what that work is. And it provides pretty good balance of partition sizes, and we'll talk a little bit about why. And finally, it provides data locality. It's putting the same values together, and that provides better compression and therefore faster queries. So the hash partitioning process is divided into 3 phases. The first phase is called partial dimension cardinality tasks. It's only necessary if you don't specify num shards. So num shards is the number of secondary partitions that are going to get created within each time chunk. You can specify that manually, and then you don't have to go through this phase. Or if you don't specify it, the ingestion will initiate this phase in order to come up with a good value for num shards. So what it does in order to calculate this is that each of the worker tasks that are spawned get a subset of the raw data to work on. They scan that raw data and estimate and read the partitioning dimension columns and estimate the cardinality of those partitioning dimensions across every time chunk that they read. Now, this is a partial estimate of that cardinality because the same values could appear in all of these raw data subsets. So we get multiple estimates in parallel from different subsets of the data, and then we need to do something to get the final estimate. So that something is we concentrate each of those estimates into the parallel index task that then calculates the highest cardinality across all time chunks. And that highest cardinality is then used in this formula to calculate num shards. You'll need to specify the target rows per segment, and it'll calculate how many partitions would be useful given the cardinality that it sees. So let's think about this a little bit. Normally, target rows per segment, the default value is like 5 million rows. So if you have 25 million as the highest cardinality in a time chunk, it will naturally create 5 sub-partitions of that, and each of them will have 5 million rows, which is kind of nice. Now, if this value is lower than the 5 million cutoff point, that means that this is less than 1, so we'll end up with a single partition. So once you've either specified num shards or calculated num shards using that first phase, we'll arrive at the second phase, which is the partial index generate tasks. So this phase is again executed in parallel. So each of the worker tasks is going to do the same job with its subset of the data, and we'll talk about one worker task and what each of them is doing. So each worker task will parse the raw data, look at the partition dimensions that you've specified, and with the values that it sees in those partition dimensions, calculate a hash, and from that hash, calculate a target partition. So which of the shards that it's going to build will each of those hash values fall into, right? And to describe this here, we've color-coded it here, where we have 3 different colors that identify which partition each of these rows will end up in. So as each of these worker tasks process the raw data, it's going to first look at the time column and send the rows either to one time chunk or the other. Within each time chunk, we see that it's subdivided it into the number of shards that we either specified or calculated, and then it starts distributing the rows across those time chunks and partitions. So it processes all of its input, classifies the rows based on time chunk, and then each individual row is put into the appropriate partition based on the hash calculation that it has. All right. So at the end of this phase, we end up with each worker having done this classification job, subdividing into time chunks and into each of the shards. But it's only going to have done it for its subset of the raw data. So that's where the next phase comes in. So in the next phase, we start with the results from the previous phase, right? Which means each worker will have subdivided the data into time chunks, and within each time chunk into subpartitions. And each of the workers will have done the same job, so it'll have overlapping time chunks and partitions that need to be merged. So in this final phase, the partial segment merge tasks, each worker is assigned a subset of time chunk partitions from the results that all of the workers did before, and it will communicate with the other workers to shuffle the rows for that correspond to the time chunk and partition that it's working on, or the multiple time chunks and partitions that it's working on. So each worker task will do multiple shuffles to produce multiple final partitions, and each of the worker tasks is doing this such that all of the time chunk partitions end up being merged in parallel across all of the worker tasks. Once this merge has occurred within each worker task, because the values are now all together for the same time chunk within the same dimension values, it can do final rollup and therefore finalize aggregations if you're aggregating as you're ingesting. And in the end, you have a fully separate subpartition of the data that has its final aggregations and that can be output to the segment file format and directly submitted into deep storage.
Okay, so let's see this in action. Let's bring in a demo where we're going to load some example data. This is 24,000 rows of Wikipedia entries. And we're going to skip over to the partitioning view, just to take the rest of the defaults. Segment granularity we keep as day, the partitioning type we set to hashed, and we set the target rows per segment to 10,000 so that we actually get some split of those 24,000 rows. We select the partitioning dimension. We'll use channel first, and let's go ahead and name this. We name this as Wikipedia hashed, so we can recognize the partitioning strategy here. And this is the resulting load spec, right, where we see the partitioning spec at the end of the spec as part of the tuning config. So let's go ahead and submit that job. It's a single task because there's a single file involved here. If there were more files, it would produce more tasks. But this single task is capable of doing the whole process of splitting into the subpartitions, and there's no need for a merge. And so let's take a look at the result here. So we take a look at the segments, and we see that these are three segments that were produced for the same time interval, and the shard spec is set to hash channel. And we can see the size of the partitions, right? And we can see here that one of the partitions is actually a lot larger than the other ones, right? There's almost 4 times as many rows in that one than in the other two. So channel is probably not the best, at least not by itself. It's not the best hash distribution column. We can take a look at the distribution within the segments. So let's use a segment metadata query with the channel column, and this will list the segments, right? One row for each of the partitions, and we see that the cardinality is pretty even among them, so that's as expected. The values don't represent much here because each value gets assigned to a different partition. There's no order in them. But let's take a look at this in more detail. Let's look at the data. So let's get a count of rows by channel from the Wikipedia hash table. We'll need to group by channel and order by the count descending, so that we see the most common values first. We see here that one of the channels, the English Wikipedia, has a lot more entries, and a few others also have a high number of entries for this day. So, and the other values are a lot less, right? So it's more of an exponential distribution here, which is not ideal for hash partitioning because the larger values will fall, whatever partition they fall into will be larger. So let's try to fix it, right? Let's edit the spec and add another column. When we add a user here, so now that we're hashing on combinations of channel and user values in order to generate the splits, this should produce a different result. Let's see what it produces. So let's name it something different, Wikipedia hash 2, and so we can compare them. So I've skipped over the execution of the job, but let's go look at let's see that it completed. Yep, it's completed. So now let's take a look at the data sources again. We'll see two data sources now. We look at the segments for Wikipedia hash 2, which is the one we just did, and we'll notice that it's a little larger total size than the other one, right? So maybe less compressible. Still the same time frame. We see the 3 partitions. Now the shard spec shows the hash by channel and user, and we see that there's a better balance, right? It's not as extreme as before, but still not ideal, right? There's still a lot of a lot more rows in one partition than in the others. So let's take a look at why. We can select now channel and user and group by both channel and user so that we see the order, so that we see the combinations of values that are better. I ordered incorrectly there. Let's order by the count. So now we see that there are a few values that have much larger row counts than others, right? So there's still some user activity within some channels that's a lot more active. Maybe they're bots or something. So this is still has a bit of an exponential form, so it's still not ideal.
So summarizing hash partitioning, it provides perfect rollup because it reorganizes the data such that the values are together, and it can do those final aggregations at ingestion time. It can provide partition pruning at query time if you're specifying in the where clause, if you specify the partitioning dimensions, where you'll be able to select a single sub-partition that has the values that you're looking for. It has a moderate ingestion speed, so it has to do a lot more work than dynamic partitioning, so it'll take it more time to ingest the data this way, but it has its benefits. It provides a good balance of partition sizes. If you think about, the hashing mechanism is distributing the data regardless of the order of the partition dimensions. It's distributing it across the secondary partitioning pretty evenly, as long as the distribution of the partitioning dimensions is also pretty even, right? If you have a single value of your partitioning dimension, or single combination of values that is highly skewed, that has a lot more data than other values, you'll end up with some imbalance in the partition sizes. So there's some dependency on the distribution of the data. But in general, it's bringing the data that's the same values together, and because the same values together and consecutively in a dimension, in the columnar structures, allow for a lot better compression that gives us faster processing and faster queries. Thanks for watching, and please like and subscribe, and check out the description for links to other learning resources.